And that is loop quantum gravity.
LQG.
LQG, exactly. And we're lucky enough to be joined by, someone who's been digging deep into this, especially Carlo Rovelli's work, which is no easy feat. So before we even get into the nitty-gritty, what is it about LQG that makes it stand out from other attempts to, wrangle gravity and quantum mechanics into a single theory?
Well, I think the best way to describe it is LQG really takes this bold stance. Instead of trying to kind of shoehorn quantum mechanics into general relativity's world, it's like, let's rethink the very fabric of space-time itself.
Okay, now we're talking. Because I gotta say, every time I read about this stuff, that's what really gets me fired up. It's like, what if our fundamental assumptions about reality are, totally off?
And that's what LQG does. Rovelli talks about this idea of no background metric, which basically means space-time isn't just this empty stage where the play of physics happens, it is the play.
Oh, okay, I love where you're going with this, but my brain needs a visual.
Okay, picture this, right? Imagine a play where the stage itself is actually made up of the actors, their interactions, their movements. It's constantly changing based on their relationship.
Dynamic.
Exactly. And that's kind of what LQG proposes for space-time. It's not this fixed, independent thing. It emerges from the interactions of these fundamental building blocks, these loops.
So not tiny vibrating strings, like in string theory, we're talking loops, but what are these loops? Are they made of loop dust or something?
Loop dust, I love it.
Right.
But see, that's the thing with LQG. We're diving down to this level where what's it made of gets seriously weird.
Right. I feel like we're always on the verge of breaking physics.
Exactly. Think about an electron, right? What's it made of? Well, it's fundamental. It's not made of anything smaller.
It just is.
It just, as LQG says, these loops, they're the same. They're the fundamental building blocks of reality, just like electrons in the particle world.
So no loop dust. Got it. These loops are the stars of the show. They're interacting, weaving this grand cosmic tapestry we call space-time.
Love that analogy. And that actually leads perfectly into the next piece because Rovelli talks about these weaves.
Weaves. Okay, lay it on me.
Okay, so you've got this beautiful tapestry, right? Up close, it's just threads, but step back, you see the whole picture, right? Intricate patterns, shapes, all emerging from these simple threads.
Okay, I'm with you.
In LQG, these weaves, they're like specific configurations of those loops. And at our macroscopic level, we see them, or rather we experience them as the smooth, continuous space-time we're used to.
It's like how a bunch of pixels on a screen can make a whole picture.
Exactly. It's all about perspective.
Perspective, I like it.
Yeah.
So if we zoom in on this cosmic tapestry to get up close and personal with these loops and weaves, what's really going on? What's LQG telling us about the essence of space itself?
This is where things get really mind-blowing. So you know how in quantum mechanics, things like energy, they come in these tiny, indivisible packets called quanta?
Right, like the energy equivalent of a penny. You can't have half a penny.
Exactly. Well, LQG says space itself might be the same way. It's not smooth and continuous like we think. It actually comes in these unbelievably small, discrete chunks. We're talking Planck scale here.
Okay, hold on. Chunky space. Now you're just messing with me. Right?
I wish I was making this up. But seriously, it's like saying those pixels on your screen, they're not just a limitation of technology, they're how reality is actually built.
Whoa. Okay, so if these pixels, these Planck lengths, are so ridiculously tiny, why don't we ever notice this chunkiness? Why does space feel so smooth?
Well, think about those pixels again. Get right up close, you see them, right? But step back, they blend together, you get the illusion of a continuous image.
So space is tricking us. It's all a big cosmic illusion.
In a way, yeah. At our macroscopic level, this Planck length is so unimaginably small that space still seems perfectly smooth and continuous.
Okay, but this chunky space-time thing, it's not just some theoretical quirk, right? This has to have some serious implications. I mean, we're talking about the very fabric of reality here.
Absolutely. And this is where LQG starts to offer some really intriguing answers to some of the biggest mysteries in physics and cosmology.
Like what? Give me an example.
All right, let's talk about the Big Bang.
Oh, you mean that little event that supposedly birthed the entire universe?
Right, that little event. So general relativity has a bit of a problem with the Big Bang.
Yeah, how so?
It predicts this thing called a singularity, a point of infinite density where all our equations just break down. Things get a little awkward.
Awkward is one way to put it. I mean, what even is infinite density?
Exactly. Nobody really knows. But here's where LQG comes in with, in my opinion, a much more elegant solution, the Big Bounce.
The Big Bounce. Okay, I am intrigued. Tell me more.
So instead of the universe starting from this point of infinite density, the singularity, LQG suggests there was this previous phase where the universe was contracting and reached this highly compressed quantum state.
Quantum state. So are we saying there was something before the Big Bang?
Not necessarily before in the way we think of time, but more like a different phase of the universe's existence.
Like cosmic do-over.
Kind of. It's like the universe was on this cosmic trampoline, hit its limit, and instead of collapsing into a singularity, it bounced back outwards. And this bounce, it's governed by quantum gravity, so no need for that messy singularity.
Okay, I have to admit, that's a much more satisfying picture than the universe just appearing out of nowhere.
Right?
But this big bounce, it's not the only thing AQG has to say about the universe's greatest hits, is it? We haven't even touched black holes yet, and those things are like the ultimate cosmic enigmas.
Black holes are definitely where things get really wild, and one of the most compelling pieces of evidence supporting LQG, at least in my opinion, is its success in tackling a major puzzle in black hole physics, their entropy.
Okay, now you're just using big words to sound smart. Entropy. Remind me what that is again.
No, I promise, it's relevant. But you're right, entropy isn't exactly a household term. Think of it as a measure of disorder or randomness.
Okay.
And you might be surprised to learn that even black holes, which seem like these incredibly simple objects defined by their immense gravity, they have entropy.
Yeah.
And a lot of it.
Wait, so you're saying black holes aren't just these like cosmic vacuum cleaners sucking up everything in sight? They've got some kind of internal messiness.
Exactly. And this entropy, it's connected to some mind-blowing physics happening at the edge of a black hole at its event horizon.
The event horizon, the point of no return.
Exactly. See, Stephen Hawking, he showed that black holes actually radiate energy, which we call Hawking radiation.
Right, they kind of evaporate over time.
Exactly. And that means they have a temperature. And wherever you have temperature, you have entropy.
Okay, so I see the connection now. But how does all of this relate back to LQG? I feel like we've gone down a bit of a rabbit hole here.
No, we're getting to the good part. Remember those chunky pixels of space-time? Those Planck lengths?
Oh, right.
Well, LQG uses them to explain black hole entropy in a really elegant way. You see, the event horizon of a black hole, in LQG, it's not actually this perfectly smooth surface.
That's pixelated too.
Exactly. It's also made up of these tiny Planck-sized building blocks, and each block, it carries a tiny bit of information.
So the event horizon is like a cosmic hard drive.
In a way, yeah. And by calculating the number of ways these Planck-sized blocks can be arranged on the event horizon, you can actually derive the Bekenstein-Hawking formula for black hole entropy.
Which basically tells us how much stuff a black hole can store, right?
Exactly. And the fact that LQG can derive this formula from its core principles, that's a huge point in its favor. It suggests that, hey, maybe we're onto something here.
Okay, that is super cool. So it seems like LQG is scoring some major points. It's tackling the Big Bang, black holes, the very nature of space itself. But is it a done deal? Are there still unsolved mysteries in the quantum gravity case file?
There are always more mysteries to uncover, and while LQG is incredibly promising, there are still some pretty big challenges ahead.
Like what? What are the biggest hurdles LQG still needs to clear?
Well, one of the biggest ones is figuring out how to connect this beautiful theory of space-time we've been discussing to the world of particle physics.
So we've got this amazing map of the universe, but no street signs. Like, we need to figure out how to navigate from this grand picture of space-time down to the nitty-gritty of how particles actually interact with this chunky reality.
Precisely. It's like we've got these two separate puzzle boxes, one for gravity, one for particles, and we're still searching for those missing pieces that connect them into a unified whole. But there's another really exciting avenue that researchers are exploring, searching for what we call loop quantum gravity fingerprints in the cosmos.
Cosmic fingerprints. Okay, now that sounds intriguing. What kind of fingerprints are we talking about?
Well, if space is truly chunky, as LQG suggests, then there might be these subtle but detectable effects on things like the cosmic microwave background radiation, which is the afterglow of the Big Bang. Imagine ripples on a pond, right? Even tiny pebbles create these spreading patterns. Similarly, the quantum nature of space-time might have left these incredibly faint imprints on the very fabric of the universe.
So we're looking for these, like, faint ripples in the cosmic pond, these whispers from the very beginning of time that could tell us if LQG is on the right track.
Exactly.
That's some seriously next-level detective work.
It really is. And the incredible thing is we have the tools to do it. Thanks to these incredibly powerful telescopes and these really sophisticated analysis techniques, we're actually getting closer than ever to potentially detecting those faint signals.
That's amazing. And it really goes to show, like, the sheer scale of what we're talking about here. We're not just talking about some esoteric theory. We're talking about the very essence of reality itself.
Absolutely. And that's what makes this field so exciting to me. We're not just testing equations, we're testing our fundamental understanding of the universe.
It's like the ultimate existential question. What is reality really made of? And LQG might just hold the answer.
It just might. And even if it's not the complete picture, even if it needs modifications or refinements, I think it's safe to say that LQG has fundamentally changed the way we think about quantum gravity.
Right. It's a game changer. And I think that's a perfect note to end on for today. But don't worry, we'll be back next week to dive even deeper into the weird, wonderful, and utterly mind-blowing world of loop quantum gravity.
I can't wait.
So last time, we were talking about this idea of, like, chunky space-time.
Right.
This idea that if we could zoom in close enough, space itself isn't smooth. It's actually made up of these unbelievably tiny, like, pixels.
Yeah, Planck lengths.
Planck lengths.
Yeah.
And I got to say that really messed with my head a bit, so I've been doing some more thinking about it.
Okay.
And one thing that keeps tripping me up is if these Planck lengths are so ridiculously small, like billions of times smaller than an atom,
Way smaller.
why don't we ever notice them? Why does space still seem so smooth to us if it's actually, like, all pixelated at the most fundamental level?
That is a great question, and it kind of gets to the heart of how we perceive reality, right? Because think about it, at our macroscopic level, that Planck length is so incredibly tiny that for all intents and purposes, space still appears smooth and continuous. It's only when you get down to those incredibly tiny scales, that quantum realm, that this chunkiness would become apparent.
Okay, so it's like our human senses are too, like, low resolution to pick up on this quantum jitteriness.
Exactly. It's like, imagine you're looking at a really high definition TV, right? You're standing a normal distance away and the picture looks perfectly smooth, but then you get really, really close to the screen, like nose to the glass close.
I hate when I do that.
And you start to see those individual pixels, those tiny squares of light that make up the image. That's kind of what's happening with space-time and the Planck length. From our everyday perspective, we're standing way back from the TV, so to speak, and everything looks smooth. But if we could somehow shrink ourselves down to that Planck scale, that's when the universe's pixels would come into focus.
Okay, I like that analogy. So we're basically living in a high-definition universe, which honestly is pretty cool when you think about it.
Yeah.
But this chunky space-time thing, it's not just some weird theoretical quirk, right? It has to have some pretty mind-blowing implications for,
Yeah.
like, our understanding of the universe. I mean, we're rewriting the very fabric of reality here.
Absolutely. And this is where loop quantum gravity, LQG, starts to offer some really compelling answers to some of the biggest mysteries in physics and cosmology. And one of the most exciting frontiers where LQG really shines is in the realm of black holes.
Black holes. Okay, we got to talk about black holes. Those things are like the ultimate cosmic enigmas, even weirder than trying to wrap my head around chunky space-time.
Right. I mean, there are these regions of space-time where gravity is so strong that nothing, not even light, can escape. But for a long time, black holes presented a major problem for physicists.
Yeah. What was the issue?
Well, one of the biggest mysteries was this thing called the black hole information paradox.
The information paradox. I feel like we're going to need a whole other podcast episode to unpack that one.
Nothing. We probably could. But basically, it boils down to this. Quantum mechanics, it says that information can never be truly destroyed. But then along come black holes, seemingly gobbling up everything in sight, information and all. So the question became, where does that information go? Does it just disappear, which would break the laws of quantum mechanics? Or is it somehow preserved?
Okay, yeah, that is a pretty big paradox. So how does LQG even begin to address that?
Well, this is where things get really interesting. Remember how we were talking about space-time being made up of these tiny Planck-sized building blocks in LQG?
Right, those little pixels of reality.
Exactly. Well, according to LQG, those building blocks aren't just sitting there passively. They actually have a sort of inherent spin to them, like tiny little quantum gyroscopes.
Whoa, okay, so space-time is even weirder than we thought. It's like a cosmic disco floor where every pixel is spinning to its own tune.
I love that analogy. But it's those spinning pixels that hold the key to understanding how LQG resolves the black hole information paradox. You see, when something falls into a black hole, its information isn't actually destroyed, it's just converted into a different form. It gets encoded in the intricate dance of these spinning, Planck-sized building blocks at the event horizon, that point of no return for anything that gets too close to a black hole.
Okay, so the event horizon is like a cosmic hard drive, storing the information of everything that falls into the black hole.
That's a great way to think about it. The information is still there, it's just stored in a way that's incredibly difficult, but not impossible to decipher.
So LQG basically gives us hope that information isn't lost in a black hole, it's just really, really well hidden.
Exactly. And it does this by fundamentally changing our understanding of what black holes actually are at the most fundamental level. They're not just these cosmic vacuum cleaners that suck up everything in sight. They're more like cosmic hard drives, storing the information of the universe in the quantum spin of space-time itself.
Okay, now that is mind-blowing.
Oh.
I mean, we're talking about a complete paradigm shift in how we think about black holes, and it all comes down to those tiny little spinning pixels of space-time. So last time we were talking about those mind-blowing implications of chunky space-time and black holes.
Yeah, black holes as cosmic hard drives.
Right. It's like the universe is just one giant information storage system.
In a way, yeah. And this is one of the areas where loop quantum gravity really gets exciting because it offers this incredibly elegant explanation for how information can be preserved even in the face of these seemingly all-consuming cosmic monsters.
Like LQG is telling us, don't worry, the universe keeps receipts.
Exactly. Information might get scrambled, it might get converted into a form that's really hard to decipher, but it's still there, encoded in the quantum fabric of space-time itself.
Okay, so this is all incredibly cool and mind-bending, but I have to ask, how do we actually test any of this? I mean, we're talking about phenomena that happen at the tiniest scales imaginable inside black holes at the very edge of our understanding.
That's the million-dollar question, right? And it's one of the biggest challenges facing LQG and really any theory of quantum gravity. Because how do you directly observe something that's happening at the Planck scale, billions of times smaller than an atom? It's like trying to study the intricacies of a grain of sand using a telescope.
Yeah, that's not exactly easy.
Right, but there are a few really promising avenues that researchers are exploring. One of the most exciting is looking for what we call observational signatures of LQG in the cosmos.
Observational signatures. Yeah, to break that down for me.
Basically, we're looking for any kind of measurable effect, however subtle, that could be directly attributed to the quantum nature of space-time, as predicted by LQG.
So like some kind of telltale sign like a cosmic fingerprint that says, hey, LQG was here.
Exactly, and one of the most promising places to look for those fingerprints is in the cosmic microwave background radiation.
Ah, the CMB, the afterglow of the Big Bang itself.
You got it. Now, the CMB is already this treasure trove of information about the early universe. It's like a baby picture of the cosmos.
And we're trying to see if there are any like LQG birthmarks in that baby picture.
Precisely. Because if space-time is truly chunky at the Planck scale, if it's made up of these tiny, indivisible building blocks, then that quantum jitteriness should have left some kind of imprint on the CMB.
So we're looking for those faint ripples in the cosmic pond, those whispers from the very beginning of time that could tell us if LQG is on the right track.
Exactly. It's incredibly subtle, but the idea is that these quantum fluctuations in the early universe, governed by LQG, would have created these tiny variations in the temperature and polarization of the CMB that we could potentially detect with our telescopes.
Okay, that is seriously next-level detective work.